A very good morning to all of you. Today we are at lecture 27 of Control Engineering AI 503. Now, what is the topic today? Nyquist stability criteria and related numericals. Till we did the GMPM calculation regarding the Bode graph as well as the in case of the what you can say the root Lucy in polar plot we done already. Almost all these are all the frequency domain representation as well as the stability as criteria that we need to establish for any control system, right? That was the prime objective. In case of Nyquist stability criteria also, we will determine the system is stable or not, that means absolute stability as well as the relative stability. That means we are going to measure GNPM as well as we will determine the system stability. We will comment on the final comment on the system stability that will be declared. Okay. So first of all, I will be describing what is basically the basic part of the Nyquist stability criteria, how it is coming from certain there are certain rules, okay, to draw down the semi-graphical approach that we generally do in case of the Nyquist plot, okay, and then we will be going through the certain numericals to clarify all those uh, concepts. Okay, let's move on. So what is the topic I have chosen for you? That is the Nyquist stability criteria basics. It is very much vital. While the physical realization of any numericals, okay, that is basically the experimentation with any kind of system with a set of values. That is nothing but numericals means what? It is one type of experiment. Okay, and you are doing basically using all those data. You are designing certain parameters, right? So that's why it is very much vital. So the concept should be very clear, otherwise you can design it. Okay, and we have to draw the Nyquist plot for any given system. And the stability analysis obviously as because it is the main objective of drawing the Nyquist plot. Okay. Now what is Nyquist stability criteria basics? See, whenever we are talking about the open loop system. So open loop system means its transfer function is representing mainly GS. This is our processor plan. Now if it is created back, so we are getting here closed loop transfer function. There is nothing but if it is negative feedback considered, what we have analyzed, that is GS divided by 1 plus GS, right? Now in that case, this is basically your closed loop system, along with this is basically the characteristics expression you can say. Okay, that is the denominator polynomial. Okay, so if it is equals to 0, we are getting the characteristics equation. Okay, as same as we have described. Okay, now in case of the when you control system having the gain, if gain it is not gain, it is the transfer function of the process of plant, that will there will be the numerator polynomial as well as the denominator polynomial. Similarly, we have HS having with numerator polynomial and denominator polynomial, right? So it is the open loop transfer function of the closed loop system we are representing, that is nothing but this factor, GS, HS, right? So we are getting here, this is basically this two multiplication factor. Now, characteristics equation will be forming with 1 plus GSHS. So, what is the modification actually? Okay, so GSHS term that is representing over here having numerator polynomial as well as the denominator polynomial, right? Now, in case of GS, if this is the denominator polynomial, so denominator polynomial mainly representing basically open loop pole positions. So from denominator polynomial of GS, we are getting basically open loop pole positions, right? Open loop pole position, that is the objective, right? So GS having as denominator polynomial, numerator polynomial as well as the denominator polynomial, right? And having with certain gain factors. That is good. That is the representation of GS. So whatever be the factorization of this polynomial if we take, so we are getting all the pole positions. So those are basically open loop pole position we can count, right? Now, if we take 1 plus GS, which is right, G divided by 1 plus GSHS. So what is the modification? 1 plus GSHS. That is basically representing the characteristics equations. So all the roots of this characteristics equation, roots. Roots of the characteristics equation that is coming in closed loop system. It is in closed loop system. What we can say? It is in closed loop system, that is Ts. So this one is Ts, right? It is in closed loop system. That one is Ts. So we are representing here Ts having the numerator polynomial as well as the denominator polynomial, right? So Ts having the numerator polynomial as well as denominator polynomial. So in denominator polynomial, what is the modification? Modification is not only Gs we have but also 1 plus Gs. And sometimes Hs is taken uniquely for most of the time, right? So in that case, what is the modification we get? That modification is that here, in case of the denominator polynomial, all the positions of the pole will change. Okay, so here the roots of characteristics equation, that is nothing but you can represent as very important concept, that is nothing but the closed loop pole position. Closed loop pole position. Closed loop pole position. So from open loop pole positions, that is declared by GS in the polynomial, and then if you just modify with 1 plus GSHS, and that basically representing the characteristics equation, right? That is representing basically the characteristics equation. And then roots of that characteristics equation, that's nothing but the closed loop pole position given. Okay, so it may be declared as closed loop pole positions. Okay, so this is declared as closed loop pole position of keys. So open loop pole position, closed loop pole position. Now it is clear again. Okay, again I am just defining with certain examples. Suppose we have GS is having it is plus 1 divided by is plus 2. So, okay, so what is the closed loop open loop pole position? So in case of open loop transfer function, we are getting that there is a pole at s equals to minus this here issue, right? It is S-domain representation and it is basically sigma j. This axis here represented, right? Now here what is happening? 1 plus GSHS if you check, and that is the denominator polynomial, right? What is it? 1 plus, why? Because total transfer function is what? Total transfer function is mainly GS divided by 1 plus GS Hs. That is written also. So we are taking 1 plus GS Hs, that part the denominator. And what is the modification? Let's see. That is 1 plus is plus 1 divided by s plus 2. Right? So what we get here? S plus 2 plus is plus 1, plain and simple. So what we get here, this is for 1 plus GSHS, this is the numerator polynomial, so we are getting here 2s plus 3. So what is the modification done? Only in the numerator of this 1 plus GSHS, that's it, right? So that is 2 is plus 3. So what is the pole position? Is equals to minus 3 by 2, right? So the pole position has changed now and is equals to minus 3 by 2. So it is called closed loop pole. Or you can say it is the, if you take it as a 0, so that will be the characteristics equation. So character roots of the characteristics equation, that is your minus 3 by 2. Nothing else. Let me clearly sketch. So that is described over there. GS, while is making basically the closed loop transfer function, where 1 plus GSH is representing basically the characteristics equation. So roots of the characteristics equation is nothing but the closed loop position of the system. So while we are making, here conception should be there. While the open loop is made into closed loop, right? So open loop pole position is fixed, but closed loop pole position that can change with respect to the system variable, right? So in that case, the modification is done in closed loop pole positions, right? So from the Nyquist plot, what we'll have to understand from the Nyquist plot, that we don't know how it will be drawn, it's coming later on. We want to find what will be the number of right hand side pole of the system that is closely pole of the system exists. Okay, that we will encounter through the encounter, right? That we will encounter. Very nice word. Encounter through the Nyquist plot using the stability criteria, right? We will encounter what will be the number of right hand side pole positions. That means the right hand side, right hand side root of the characteristic equation. It may be sometimes termed as, if we are taking only 1 plus GSHs, that part, 1 plus GSHs, that part. So this is the numerator that we will regard it as zero source. Zero source. Okay, but closed loop. Okay, keep it in mind. Closed loop. So, so here, if there is any closed loop pole on the right hand side, right part of the plane, the system will be unstable, obviously, right? If it is in right hand side pole, then system will be unstable. If it is left hand side pole, then system will be absolutely stable, right? So in this way, we will encounter, our objective is to encounter basically the right hand side pole positions. Pole, main, right hand side pole. What will be the number of right hand side pole? Okay. Then from the stability criteria, also using the concept of polar plot, we will draw the Nyquist plot, as well as we can find out what is basically the gain crossover frequency and phase crossover frequency, along with the gain margin and phase margin. So it is the total package, you can say, that may be utilized for the stability criteria analysis, and it's very easy to, it's very easy to realize. Okay, let's move on. What we have here, see, while we are going through the Nyquist criteria, so before going to the direct criteria, let's find out what is the concept of contour. Because in case of the Nyquist criteria, if we have to establish, we means basically the theory of arguments by Cauchy, scientist Cauchy. Okay, so in that case, we are using basically the fundamentals that will be described. Suppose the system having this kind of what we say pole and zeros positions, declaring there are two zeros, there are two poles, same as static. Okay, so it is the representation of the closed domain representation. Suppose it is we are considering a contour over there. Okay, now we will be analyzing this uh, having all the zeros and the poles. Each zero is included by our assumed contour, and which zeros, which poles are including or excluded by our assumed contour. Okay, so let's say it is our contour. We have assumed it. Okay, now just see, as it is basically the position of S showing. Now, if we are just replacing that S domain function into Fs domain function, that means each of the S value we are putting as a function of treat F as a Fs as a function of S, right? So we are putting a particular value of S. Suppose it is S equals to 2 plus J, right? So we are putting a particular value of S at that function. So what we get here, there is a particular phasor, right? So for a particular phasor in H domain, there is a particular phasor in the F domain, F plane we can represent. That means it is domain to domain transmission, or plane to one plane, S plane to another plane transmission. Okay, so we are finding here there is a assumed contour, and each of the point of the contour on the contour that we want to map here, and here our assumption is one point that will be mapped to that contour singly. That means one point that will be mapped here, a single point in the mapped contour. Okay, so mapping is very much important in case of the Nyquist plot mainly. Okay, so as well as understanding of the theorems. Okay, so if we consider here, this one is the contour, and all the position of the peripheries that we are considering, and that will be mapped over there. So we will find another contour, right? As we can say, it is basically S minus J1. So it is a phasor representation. So while it is representing in fs domain, f plane, so it will basically form a country. Okay, and that origin should be here 0, right? That means it will be 0 plus j0, right? 0 plus j0, and we are getting here domain to domain transmission, Q to Q dash domain transmission. So from starting from S plane, S all the points that will be considered over there on the control, and that will be mapped here. Okay, so it is called the mapped control. Okay, we are understanding how the mapping will be done. Now, for each of the specific value of S over the periphery, that will be mapped over there. And it is single point basically mapping, right? But if we want to understand over there point of singularity also. Okay, so point to point mapping is done, mapping will be done. And in case of mapping, point to point mapping we want to consider. Point to point, single point, that will be transmitted into single point, right? And there is another understanding should be there. So here, what you get that basically point of singularity, very much important concept. Point of singularity, you must have to know what is point of singularity. See, if we put s equals to p1, so what will happen? What will happen? What about the function value? We are getting infinite, right? We are being infinite. So we will discard it. For while we will be doing the Nyquist plotting, we will discard the point. So point of singularity will not be considered point while we will be taking the Nyquist mapping technique. Okay. So point of similarity means why we have all the given poles, opposite pole positions. So we must avoid that pole position. Okay, because it will break the control, right? As because C, if we put the value of Q1, so what we get the value of S, because that will become infinite. So there is discontinuity. So that should be avoided. That should be avoided. Right. So point of similarity is the important concept here also. Now let's move on. What is point? Let's see. So sorry. Now what we have to understand. Suppose we have considered this is our contour A. Now we are mapping that contour into imaginary plane, and that is our F plane. Suppose that Z1 is not included within this contour. So it is not basically enclosed. So there is another important concept is that enclosed. Enclosed means what? Encirclement that will be done over there if there is no inclusion of this point. Okay, if there is inclusion or it is excluded in the area or included. That is called outside the contour or inside the contour. So if it is inside the contour, that will be termed as enclosed, right? Okay, enclosed. Enclosed or not enclosed, right? So if Z1 is present outside of that contour, if we are finding Z1 as, or we are finding that Z1 is just outside of the contour, let's imagine what will happen. So S minus Z1 we are plotting basically, right? So in that case, it is a phasor. So what will get? What will get? For each of the point if we consider, this one is the origin, Z1, for it is that function, right? So if you put all the values, so what you get? You will get our country that is starting, very much interesting fact, our country that is starting over there. Suppose this one is the point we have started. So put the value of this one. Then we are giving the magnitude, right? Magnitude is basically the distance from the origin. So we are plotting over there. This is basically starting point. Then we are moving to that point. So our so in this way we are moving to that point. So ultimately what will happen? So again it is finally move back to that point, right? So while we are plotting, mapping is done. So what will happen? What we find? We have started over there, and we are getting like this way, like this way. Just uh, taking the observation, it is like this way. Okay. So here, what we have? This. vector is moving and it is covering as a whole the surface and it is back to the point, initial point. It is the initial point. It is the initial point, right? So what we get here, there is no encirclement about the origin, right? So we need to define an encirclement about the origin. Similarly, if there is irrespective of poles and zeros, if there is any point, that is we are considering if there is any point. Okay, it is just outside the contour. So what will be the position? What will be the basically fact that's happening in the math contour? So what is our understanding now? Our understanding is that whenever there's a point that may be pole or that may be pole or that may be zero outside the contour exists. So what will happen to that? What if it is the initial position of the vector? So it will happen that the value covering ultimately it will end up to here. Okay, ultimately it will end up to here. So what you can say, the 0 degree, 0 degree, what you can say, 0 degree formation around the origin. So that means it is not including basically the origin. So there will be no encirclement about the origin. That is our understanding, right? If the point that will be pole or zero outside of the contour, so there will be no what you can say that there will be no encirclement of the math contour that will form just with respect to the origin, right? To form. Similarly, if just opposite of the thing that if there the poles or zeros exist or any point exists within that contour, then what will happen? What is the angle made by this vector while it is moving from one point to another point of the contour? So it is clearly showing that it is moving continuously and is making 360 degree as a whole 2 pi angle it will make. And that means there is an encirclement about the origin in the map control form. Okay, okay. So as because it is the origin, so that's why it has started and it has been again rotated and again ended in back to there, right? So ultimately it will rotate and again in back to there. So ultimately what is the angle formation with respect to the with, while we are considering the origin, we are getting 0 degree. Here the encirclement we are willing to find. So even if it is pole or zeros, whatever exists within that uh, enclosed area contour, then we will get the encirclement about the origin. Okay. So for each of the points we are getting 2 pi. Then because it is a single vector we are considering, right? Now if there is the poles and zeros, whatever exists, so for each of the point we are getting encirclement about the origin. And if we are considering our contour is moving just clockwise, that means we are shifting our points over this periphery, basically this periphery, that is the contour periphery. So what we are getting here, 2 pi is the angle made by each of the point, right? Each of the point inside the contour. So obviously exists inside the contour. So if there is 2 points, so there will be the two encirclement. Now fine. While we are talking about the pole and zeros, now come to from point to pole or zero, we are more, that was general discussion. Now we are going towards specific. Now, if we are considering here any pole, okay, or zeros that is existing. So, for the pole, what we consider here as because our contour direction that is clockwise we are considering, so that's why for the pole we are using 2 pi and that is the angle made by 2 pi means clockwise movement, right? So we are getting here the encirclement about the origin and the angle is formed, that's 2 pi. Similarly, if there is any zero exist, so obviously there will be the angle made by 2 pi same, right? So it is also in clockwise direction, it is also in clockwise direction, right? But as the pole exists in the numerator and zeros exist in the denominator, so what will happen? So what will happen? Okay, so pole is making the angle 2 pi, zero is making the angle 2 pi, fine. If we consider only a point, but why we are considering the concept of pole and zeros and their existence in the system, okay, where zeros are in the numerator and poles are in the denominator. So zeros is contributing minus 2 pi and pole is contributing plus 2 pi, right? So what will be the total angle contributed by the system? That is, if we take 2 pi as common, if the number of pole is p and number of zero is z, then what we get here? 2 pi, that pole is providing basically positive angle, and that's why p is the number total. What you can say, angle is 2 pi p, it is the number of pole axis, and if zero is the z is the number of zero axis, so zero is giving the negative angle 2 pi for each of the zeros. So z, if the number of zeros exists, so we are getting 2 pi z as a total, what you can say, the angle contributed by zero. So accumulating poles and zeros, we are getting the total angle. Okay, total angle that will be argument, that will be equals to 2 pi p minus z. Okay, p minus z, and that concept is coming from the, and that is suggesting there will be the p minus z number of encirclement, p minus z number of encirclement, if encirclement we are taking as n as well. So p minus z number of encirclement about, very much important concept, origin in the math control will happen. Okay, so this is the important concept that is built up to go into the depth of the Nyquist criteria. Let's move on. Let's say in our characteristics equation, we have this much number of poles and zeros exist, right? So what we get here in our system that exists in the explained PZ map is showing basically. So first step is PZ map, okay. Then second step is what we are doing, mapping, okay, mapping in the Q dash domain, or you can say it is fs, okay, domain, anything else. So now what we have established from the what you can say, the principle of argument, that is called Cauchy's argument principle. Okay, what is the total angle? Total angle will be 2 pi into p minus z. Now if n is the encirclement about the origin, okay, and that we are considering here clockwise encirclement, so what you get here, that will be basically, if it is clockwise, that means it is basically negative angle, right, according to our concept. Because see, the angle concept is that always the positive angle will be with respect to x axis, that will be anti-clockwise. So that's okay. That is the same issue over there. So that's why we are getting here 2 pi cancel. We are getting total number of encirclement about the origin, that is basically p minus, and n will be considered as positive direction. So positive direction, that means what? Counterclockwise direction that you have to consider, right? And p is the number of pole that exists, p is the number of pole, and that basically it will be termed as open loop pole. So p is nothing but your open loop pole position, open loop pole. P is the number of open loop pole, and z is basically number of pole of, number of basically number of closed loop poles. Okay, now number of closed loop poles. So it is nothing but you can say roots of the characteristics equation, right? That we have established that concept, roots of the characteristics equation. Okay, so that's why P is the number of open loop pole. So from PZ map, you can easily opt what will be the number of pole. But zeros, while you have to consider, again there's a technique of basically how to encounter what will be the number of zeros that exist in the right hand side. Okay, that is coming to that point. So here Z is basically closed loop poles. Okay, it will be on a next sketch. So here the Cauchy's argument, principle of argument, that is showing basically e minus z into 2 pi, that is basically 2 pi n. And obviously the stability criteria over there is that in the encirclement about the origin in the fs domain or q dash domain, that will be equals to, that should be exactly equals to p minus z to get the system stability. Okay, And rather that this more general case is that P at the right hand side, that is openly pole existing for a stable system generally at the right hand side there is no pole. Right hand side there is no pole. Okay. It is not basically for all case but in general. Okay. So that's why we can put another one, that is z equals to basically minus z. Okay, z equal to basically minus z. Okay, so number of encirclement, that will be clockwise in that case, that should be exactly equal to the number of zeros existing in the system or number of closed poles existing in the system. Okay, so this is all about the principle. And now regarding the Nyquist control. So how to suggest the Nyquist control for a specific problem? Okay, then we have to understand. Because see, in case of while we will be dealing with certain numericals, so you have to find the concept. First of all, what you have to do first step? First step is PZ map. Okay, so from the PZ map, what you are encountering, that is what is the number of pole exist at the right hand side. What is the number of pole exist at the right hand side? Thirdly, you have to encounter to actually to count Z, you have to find N. And n will come from the basically your polar plot, or you can say Nyquist plot. N will come Nyquist plot. Then we are just we will be just putting all those values of p's and n's. In this case, in this expression, we are finding basically z. We will be finding basically z. So this is the technique. So first is PZ map, second is mapping, and then PZ map, from PZ map we are finding basically what will be the number of pole at the right hand side, openly pole at the right hand side. It is generally not happen in case of stable system. And then from basically polar plot we will find n, and from where we will find z by using this expression as it has already established. Okay, so let's see if for a system having what you can say no pole at origin, no pole at origin or along the geometry axis, if there is no pole. So what you can find, what you have to think, you have to think that there will be a contour. Okay, and what is our suggestion? What would be our suggestion is that it's like a net that we are basically spreading the net to catch the right hand side closed loop poles. To catch the right hand side closed loop poles exist in the system. Okay, or you can say Z existing in the system. Okay, so that's why here throughout the geometry axis, as well as throughout the right hand side of this plane. That means this is basically the for unstable system, unstable system there may be existence of the poles at the right hand side. Okay, so that's why just we are considering the contour as a whole the right hand side which is existing and throughout the geometry axis, right? So while throughout the geometry axis, so what you have to put here, here this kind of for this kind of mapping technique we have to put throughout the we can just divide this contour into different parts, say starting from origin to A. This is A part. Then we have a arc, and that is existing throughout the geometry, throughout the right hand side, right hand plane, right, of his plane, right hand side. So we are giving the arc name by three variables, that is A, B, C. Okay, and then from C to O, again there is j omega axis. Obviously, we will be putting here s equals to minus j omega while we are mapping. Then for this case, we will be putting here s equals to j omega. Right? Now, what will be the omega range of omega? Range of omega for both of these two cases, starting from 0 plus to positive infinite for s equals to j omega, and it is just mirror reflection. So while we are taking basically this part, mapping will be done. So you will observe that this is nothing but the polar plot. So that's why polar plot already done. We will be utilizing the polar plot over there while we are having with a mapping technique. Mapping will be done, then we will be utilizing the polar plot, and the omega range will be 0 to infinite. And for CO, that means we will be moving like this way. Because keep it in mind, it is the vector of phasor quantity. Phasor, always. Okay, as because you are considering as domain, right? So from uh, O to A, right? Omega is starting from 0 to infinite. Now for C2, what do we consider? Sorry, S equals to minus J omega. You are considering while omega is starting from minus infinite towards C, right? Sorry. So you are considering here. Now for ABC part, it's very simple. As because it is R, so how would you represent? S should be equals to R e to the power J. But here, what will be the range of R? R should be limited to infinite, right? As because we are putting as a whole S domain right hand side, right? So that's why R should be infinite. And what is about theta? Theta should be from plus 90 degree to minus 90. That is our arc. Very simple. This is our arc. So we are considering here the arc that is having plus 90 to minus 90. Okay. And we have here, this is the geometry axis, this part. It is enough you to draw the polar plot of this one. So this will be the mirror reflection. Okay. So obviously we are considering another uh, region, and that is the negative geometry axis. Right? So these are the parts we need to consider while we will be mapping the contour. Right? Now, move on. Let's see. Let's clear my sketch, and we will be moving on to the next part. Now, if the system having uh, that was the type 0 system, right? So if the system having pole at origin, or maybe pole on the geometry axis. So we know that pole is nothing but points of similarity that we have discussed. Pole is nothing but point of singularity, right? Singularity, right? So point of similarity we will not consider because it will discontinue. Function will discontinue in that case. If you put the value of its pole position, then we are getting GS as infinite, right? So that's why we will be not considering that point of singularity, and that's why we will be avoiding that point. Okay. Otherwise, your contour must be a closed one. Okay. Otherwise, it will be not a closed path, right? So we are avoiding that pole position. So PZ map is very much important. After getting PZ map, we have the concept that this pole should be avoided, this position should be avoided. So how to avoid it? So we will avoid like this way. That will not hamper our Nyquist mapping process. So that's why we are considering this part. Okay. So here S will be equals to, for AB part, it will be equals to j omega phi. Omega is ranging from, again, same 0 plus to infinite. Very nice. Now for this part, we have r e to the power j theta, as same as the previous, and where theta ranging from plus 90 degree to minus 90 degree fine, right? So it is the range of theta. R to the power j theta, r tends to, r limit tends to infinite, that is written over here. R limit tends to infinite, theta will be plus 90 degree to minus 90 degree. Okay, and for s equals to during the positive geometry axis, for s equals to negative geometry axis, s equals to minus j omega, and that is the E part, and that is coming s equals to minus j omega, or it is the mirror reflection of this particular part, right? So, and that will be minus infinite to 0 plus 0 minus. Okay, that is the path, and this is larger arc. Now we have to consider the smaller arc. We have to consider the smaller arc. As we are considering the smaller arc, so what you get? This is also arc. So you can represent it like this way. There will be radii of arc, to the power j5, suppose j5. So what do you get? So if you are getting here r is the j5, so r should be tends to 0 because it is we are just bypassing the origin. Okay, we are just bypassing the origin. So r should be tends to 0. And what about pi? Pi should be, it is tending towards minus 90 towards plus 90. So it will be minus 90 degree to plus 90. Okay, whether you consider minus 90 to plus 90 r tends to 0. Here r tends to infinite, but it is coming from plus 90 to minus 90. But while we are talking about this part, so it is moving from minus 90 to minus 90, is coming minus 90 to plus 90. Okay, minus 90 direction to plus 90. Okay, it is coming. So that's why this all about we need to consider whenever we are going to the mathematics. Okay. Now, what we will encounter? We will get if this is the scenario and we are getting this kind of mapped control. So we can conclude that here minus one. See, another concept is here. What is the concept? That basically suggests we are not interested at all regarding the encirclement about origin. Let's see why this important concept is coming. As because we are dealing with, we have dealt with 1 plus GSHS, right? Till now, 1 plus GSHS, that was basically what is the origin? Origin was 0, 0. Now, while we are talking about GSHS, that is very much simpler. Okay, because we don't want to form 1 plus GSHS, that will give you complex stuff. So that's why we are taking only GSHS. So what will be its origin? What will be its origin? Its origin will be minus 1. As because you know, GSHS, that is basically coming minus 1. So you are getting here minus 1 J0. So that point is very much important consideration. Okay, J0, that means on the negative x-axis minus 1. Okay, minus 1 J0 is an important concept. Okay, where we are taking into consideration our contour, our closed contour that has formed, encirclement that has formed in the GSHS plane, and that should encircle about that our side should be encirclement about minus 1 G0 point, right? Why? As because we have dealt with 1 plus GSHS, but we will be dealing with through the numerators that will be GSHS. So what will be the origin? Minus 1 G. JZ. Okay, that will be the origin. About that point, we need to find the encirclement. That's the concept. Okay. So, if it is the concept, so what is the number of encirclement we found? We found number of encirclement is equals to 0 over there. Okay. We will find this mapping technique. Okay. But in this case, we are getting here one time, then second time, that number of encirclement is 2. And as generally the system having no right hand side pole for both of these two cases, then how stability will be declared? See, what was the formula? Formula was P minus Z, that is equals to N, right? Now if N is getting Z, P is getting Z, so what will be the number of zeros existing in the system at the right hand side? That is the closed loop pole position, that is basically 0. So there is no right hand side closed loop poles of the system. So our system is absolutely stable for this case. But here we are getting here n equals to 2. So we need to find here what will be the number of zeros existing at the right hand side. That is basically 2. If we put the same formula here, we are getting z equals to 2. That means what? We have two right hand side closed loop pole at the right hand side closed loop pole existing in the system. So system is mostly unstable. And for the previous case, system is stable. So that is the total procedure. First of all, you having with the transfer function, having with the function GSHS, then you are looking just the open, what you can say, it's a PZ map. From where you are determining the value of P. Then just take the help of mapping, and you are getting the encirclement about the minus 1 J point you are calculating. What is the number of encirclement you are getting? Okay, now put the just values of all those P and N in the Nyquist stability equation, and you easily get what is the number of zeros existing, or what is the number of, basically Z means what, closed loop poles existing in the system. Okay, let's move on. Now, after getting the stability declaration, what will be its characteristic parameters? As GMP you can calculate. So how to calculate? It's very simple. See, it was done in polar plot. It was done in polar plot where G means what? G means 1 divided by G, J omega phi and Ej omega phi. What is omega phi? Omega phi is basically the phase crossover frequency. That means what is phase crossover frequency we need to find, and then we need to find the magnitude at phase crossover frequency. Okay. So what is the concept of phase crossover frequency? When the reference minus 180 degree touched by the phasor, right? So minus 180 degree is that point. So here the phasor is crossing basically minus 180 degree. Okay, that means this point. Okay, so what will be the magnitude at that point? That means this is the intercept we need to find. So OA, suppose this is the intercept we need to find. Okay, we need to find. And then if it is less than 1, then 20 log of OA, if it is factor. So what we are getting, basically minus 20 log of OA, that will become positive. So GM will be declared here positive. It is a factor. Okay. 1 divided by this row, that is minus 20 log of 4. If it is a fraction, so we are getting here positive GM. Right? It is very clear conception. So we need to find here using the polar plot technique. We intercept. Intercept of the phasor with respect to the negative x-axis. That is minus 180. Okay. This is one. Now what is PM? How to calculate? PM means what? We have to find basically the gain crossover frequency and the respective phase. So how to find? Very simple. Gain crossover frequency means our reference is 0 dB, right? 0 dB in case of log scale, in linear scale it will be unity, right? So that's why what we can say, this is basically unity circle that is representing 0 degree reference, right? So while our phasor is crossing 0 degree, the respective frequency that will be turning us basically the gain crossover frequency. And what is the respective phase? This is the respective phase. Just calculate this phase, or you can take the measure with the protector, so you will get your phi. So that alpha, that's representing over there. So 180 degree distance from 180 degree, that is basically PM concept, right? So 180 degree plus 5, you are getting basically the phase matching. So in this way, you are calculating within matching and phase matching, and that will complete your task regarding the parameters of the what you can say, the uh, microscope. So what is the example numerator? Plain and simple, I set here all the steps. That is well tape, starting with the well tape, then we have phasor map, then from where we are getting value of t, and then we will be mapping using mapping technique. We will be moving towards the QS domain, from where we are getting the value of n. We will be calculating, and then we will calculate the value of c. Fine. So if it is the example given, so how to get? What will be our contour? It is the suggested contour. It is the suggested contour, right? As because there is no pole at origin, so it is the suggested contour. Oh, now there is a pole at origin, so we are considering here this one is the suggested Nyquist contour. Okay, so we will be starting with the Nyquist contour now. Okay, let's. This is the Nyquist contour. So for this part, the mapping will be done. That is S equals to j omega we will put, and we will draw the polar plot of this case. So what we get here for S equals to, this part will be the mirror reflection of this part, right? So for this case, we are getting, this one is basically the polar plot starting from minus 90 degree, 90 degree, sorry, it is this part, A part, right? Is the E, B, C, right? This is the C part. Okay, C part. So it is 90 degree minus 90 to 0. That is done in polar plotting. Okay. With the angle, it is minus 90 infinite with the angle minus 90, it will come 0 with the angle minus 180 degree. Okay, and then mirror reflection will be there. So it will start with 0 plus 180, and then it will come to end infinite with plus 90 degree. Okay, so this is the polar plot of these two parts, C and this part and this part. Okay, so first part is there, this one is the solid part, and for this part it is dotted. So it is the dotted part. Now come to that point, this one. So for this one, what you have to put r e to the power j theta. If we put r tends to infinite, what will we get? Let's see. If we put r tends to infinite, what we have, what we have, r tends to infinite, we will get zero value. So after having the value zero, that means it is submerged on the in the origin, right? So we are not bothering with that larger arc. Now come to the smaller arc. So in that smaller arc, what you have to put? You have to put smaller to the power j theta. So if you put and r tends to 0, right, what you get the magnitude of the gs, that will become infinite. As it is infinite, so it should be infinite radius of r, right? Now what about the theta part, angle? So e to the power j theta. That means cos theta plus j sin theta, right? So cos theta plus j sin theta, you have the face, that will be basically tan inverse of tan theta. So it will become u theta, right? As it is in the denominator, so each of the s is contributing basically theta. S part, that means 1 by s part, it is contributing theta, right? Okay, now for the 1 plus s part, right? There is another part now. Let's see what is the part here. S plus 1. So we are getting s plus 1 part. So for s plus 1 part, what we have to put? We have to put here small r e to the power j theta plus 1. So that means it will be r cos theta plus rj sin theta plus 1. Right? So that's why it's having the real part, two part. One is 1 plus r cos theta plus r j sin theta, right? So it having the angle that is minus tan inverse of r sin theta. Sorry, that was also r. Okay, but r cancel. That's why we are getting tan theta only. Right? That is missed. So tan inverse of r sin theta divided by 1 plus r cos theta. Right? Now if you put r tends to 0, so what are you getting? The angle contribution 0 degree. So for latter half, the angle contribution is 0 degree, but for the smaller part, pole at origin, we are getting the angle contribution 1 by theta. So angle contribution by as a whole, that will be minus theta. Now range of theta specified for the smaller part, that is minus 90 degree to plus 90 degree, right? For the smaller part. Minus 90 moving towards plus 90. So that's why, yeah, the angle contribution as a whole will be plus 90 as because minus theta to minus 90. So you have to draw a radii of arc of infinite with the angle starting from plus 90 and then to minus 90. So let's see what is the diagram we got. So we got this kind of diagram where starting from here it is moved to 0. Then starting from here it will move to infinite. Then with the infinite radius of arc it is moving up to V. Okay, cover it as a whole right hand side. So this is the next map plot. Okay, not continue. But see, here there is no encirclement about minus 1 degree point, right? So we are finding here absolute V equals to 0 and P equals to also given 0. So what will be Z? Z will be 0. So you can easily declare your system is stable. In this way, you can solve all the problem. Okay. So that has described. So you are just doing this way and you are getting basically this is the solution. Okay. Now, if by any means, you are getting this kind of graph. This kind of graph. If you are getting this kind of graph and you are getting this kind of graph, and you have here, uh, you have to calculate basically the intercept to find out the element about -1 0 point. Okay, so you are getting here intercept -1 0 point. You have to find out, right? So intercept you are calculating. If it is less than 1, fine, your system is stable. But if this intercept is greater than 1, so it is including basically -1 j 0 point. So that will be in two times in clockwise direction. So you are putting here clockwise direction means it will be -2, right? So what you get? P equals to 0, Q equals to -2. This is clockwise direction, right? And you are having with z value that is equals to -n, that is equals to minus of -2. You are getting number of 2. Number of two closed loop poles existing at the right hand side. If you are getting this kind of polar plot. Okay, mapping, after mapping. So thank you for today. We have ended with lots of information. How the Nyquist, what is the basics of the Nyquist criteria, and what is the principles of argument. It's very much vital to go through the Nyquist criteria, as well as how to select the contour for a specific problem even, and as well as you have to draw how to mapping how the mapping will be done, and then from where you are just collecting the data of insert element about -1 0 point, if there is any insert element or not. So you are finding that number of insert elements, and from PZ map you are getting basically the number of the pelvic pole positions, and using that Nyquist stability related formula that is coming from the principles of Arduino, that is A equals to P minus Z. Okay, now from where you are calculating the total number of right hand side pole, closed pole existing on the right hand side of the display. Okay, and you are declaring accordingly your system stability, as well as you can find in the GM10 that I have described here. So thank you for today, and next class will be for state variable. Okay, so thank you.